All right, party people. So as you requested, by popular demand, right? We voted. Here's our exam two review. And we're only going to just go over the exam two review today. So you can ask whatever questions you have. Yeah, you've still got, almost 5 full days to study for it, right? Actually, you have 6 days, right? Because it's going to be on Wednesday during lab. So you do have time. And if you have a last minute question or two on Tuesday, that's perfectly fine. So let's get started. Whole zero maps, we did that a lot so far, right? We keep coming back to that topic, which seems interesting because it's a pretty trivial topic. When you think about it, it's a map with poles and zeros, right? It doesn't seem that complicated. But what we're starting to do a little bit as part of the design effort, and we've been talking about, let's stay in the left-hand half plane. What about if we move away from the J omega axis? What if we move away from the real axis? We can start to talk about performance characteristics. And so we keep coming to that to say, what are we doing? Because a lot of times you're going to look visually at a system, and we'll see that in our next topic after steady state error. We'll actually look about how to develop modified plots to get a lot of design information that we can specify. So we did it again this semester, right? And we've done it 2 or 3 times here, but just to summarize, we have Bible stability, bounded input, bounded output, which means all poles, if it's Bible stable, have to be in the left-hand half plane, not on the J omega axis, that doesn't count. But Bible stability is all in the left-hand half plane. When you're there, you've got a stable system, and you only look at the poles to address stability. The zeros you don't look at. Remember, the zeros are the roots of the numerator of the transfer function, and the poles are the roots of the denominator of the transfer function. And the denominator is what really determines the system characteristic, what it looks like. And so it's so important, we actually determined, we came up with a term called characteristic equation. It characterizes the behavior of the system. So we're really interested in the numerator of our transfer function. And the denominator of the transfer function. And it's really kind of silly to say this, but remember, there's a numerator and denominator here in our transfer function. But in fact, if we did some block diagram math, we actually have a numerator and a denominator, and a numerator and the denominator, perhaps, right? We can have fractions there. So when I'm kind of being silly, a characteristic equation is the numerator of the denominator. Look at that, right? It's actually, this is what characterizes it, because when we invert and multiply the D2, it goes up into the term there, and usually cancels out all the D1 stuff. So poles and zeros, we have finite poles and infinite poles. We'll never have a system that has infinite zeros, because any real world system will always have more poles, or at least the same number of poles as zeros, finite poles. And so the difference between the finite poles and the finite zeros has to be the infinite number of poles, which is another way of saying is the number of poles in any system, when you include finite and infinite poles, is always going to be the same. Okay. And the infinite poles are as S approaches infinity, then my system is going to approach, my pole, it's going to end up with a term, right? It's going to be S equals, we're going to end up with a 0 essentially. Okay. So, yeah, we can go ahead and look at that. That's pretty much it for pole zero maps. Any questions about pole zero maps? Again, focusing on stability, left-hand half plane, all poles are there. It's a stable system. Any on the J omega axis, it's a marginally stable system. Any pole in the right-hand half plane means it's an unstable system. It doesn't matter if you have 500 in the left and 1 in the right, it's still going to be an unstable system. Then we started doing some design, right? So we've talked about first order systems last semester. We looked at what a first order system is. It's essentially a device from an electric circuits perspective that you have one charge storage element. You can store electrons, or you can store magnetic field or energy in the magnetic field. And so we would have one of those charge storage devices. In the mechanical system world, right, we started modeling mechanical systems a little bit. And we looked at, once you had momentum of a device, you were storing energy. So it's the same concept, right? It's an energy storage. And so when you think about the number of the order of a circuit or the order of a system, it's how many different energy storage devices do you have? Maybe that's a better way to say it more generically, right? We start off in electric circuits because we're more comfortable, but we can expand that to any system. Now, that doesn't necessarily talk about batteries, because batteries are usually intended to be a source, right? So it's a chemical process and it is an energy storage device, but ultimately, most of the time, we treat a battery as a constant power source. Whereas an energy storage device that we're talking about here is something that is going to have limited capacity, meaning eventually it'll be completely discharged. Now you can say the same thing about a battery, but again, we're just trying to simplify things. So we're assuming that that battery is always going to be charged. Otherwise, our voltage is not constant. So the key things here, we have time constant, T sub C or tau. If you remember back from your circuits 1 or perhaps circuits 2 classes, that's just going to be equal to 1 over A, where A is one of the roots, right? It's one of the roots of that first order system. That's the only root, actually. And then once we know what A is equal to, we can solve for rise time, which is the time it takes to go from 10% to 90% of its final value. And then we also have the 2% settling time, which is just going to be the amount of time it takes to get to within 2% of its final value. Doesn't have to reach steady state, because ultimately it never reaches steady state, right? We say 5 time constants or 7 time constants or 3 time constants. But here to simplify, we'll just call it settling time of 4 over A. And we really wanted to develop those because for second order systems, which is our next topic, that's a lot more useful to understand those terms, especially settling time, because settling time is a little bit different in a second order system. Some second order systems can overshoot our steady state value. And so they can oscillate about that steady state point, which will give you a little bit of confusion. When does it reach 2%? Does it reach the first time it gets there? Or how about the second time or the third time or the fourth time? No, it's the last time. The last time it goes less than 2% of its final value, that's our settling time. So we spent a lot of time looking at second order systems, and we sort of formalize them with a bunch of different terms. We developed this term zeta, which is our damping coefficient or damping ratio. We developed omega sub n, which is our undamped natural frequency. And we developed omega sub d, which is our damped natural frequency. These are only important to you when zeta is greater than, is less than 1. Why? Because if zeta is greater than or equal to 1, you do not have a system that oscillates, right? So you have no frequencies. If the system is, if the damping ratio is equal to or greater than 1, then you have 2 first order systems. So you can just use the analysis that you did in section 2, just figure out which is the slower of the 2 time constants. But with that being said, you have a bunch of equations here. These I would just write down on my note card. Okay? I wouldn't even bother trying to memorize them. I would just write them down. And I'm giving you them here because it makes it really easy to find. Percent overshoot, T sub P, which is my peak time, and T sub S, which is my settling time. Those 3 equations. Now, more often than not, it's better to solve the first equation here. We'll call this number 1, because this only has the term zeta in it. It does not have any other term. When you look at T sub P and T sub S, you have perhaps 2 unknowns, zeta and omega sub n. So if you have a way of getting what zeta is equal to, then you can use that to solve for T sub P or T sub S, right? Or not T sub P, T sub S. You can solve that for omega sub n. And the reason why you're doing that is because as an engineer, if I'm designing a new suspension system and it's, you know, a Rolls Royce where everybody wants a really smooth, plush ride, I want very little overshoot. I don't want the car to be bouncing back and forth like that, right? So perhaps I might have a percent overshoot to be like 2%. Okay. And I'm okay allowing a longer time to reach a stable point because I have other dynamics in my system to do it. So I might have a very rigid requirement to be within, have less than a 2% overshoot. And then the settling time is, all right, my systems in my vehicle can only respond or can only keep the car in a good condition for 10 seconds. So it has to be within its settling time or 2% settling, 2% of its final value within, let's say, 10 seconds. So you have two design criteria, which will allow you to specify zeta and omega sub n. And then you go back to your dynamics of your struts or the shocks or whatever they are. And then you can dial in parameters, because the struts and the shocks will have different parameters. If anybody here is in the sports car, you can usually transfer and change the performance characteristic if you want it to be track mode or sport mode, which stiffens the suspension. All that's doing is it's changing some of the parameters inside the vehicle. There are more permanent ones you can do. If anybody knows about coilovers, they're for if you're really into cars, you can replace the springs, which you can make their car a lot rougher ride. But you also have an ability that you can rotate these, I don't know what they call, discs that compress the spring more, so the car actually rides a little lower, which, if you're into looks, maybe somebody likes a lower ride. But what's better about lowered springs is it's a stiffer ride, which means it's much better at taking corners, right? You don't have as much sway in the vehicle. And so that's part of the design. Maybe you're going ahead and you're trying to adjust that disc height to make sure that you meet the performance specification. Okay. Very different from a Rolls Royce to, I don't know, what's a fancy sports car everybody's in love with right now? Koenigsegg, maybe? What's that? McLaren? I thought McLaren was falling out of favor, but I don't know. It is a little bit?
A little bit, but they're still up there.
Oh, okay. Okay. Anyway. So that's how you use these equations, right? We're trying to get performance requirements. And that's a lot of what engineering is today. When you build something, and again, it depends a little bit on the something, but when I used to work with designing power plants, what we would get are a bunch of specifications from the buyer. I need you to produce 500 megawatts and this and that and da 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 da. And so you'd start backing off and figuring out how to adjust things so that you could meet the performance specifications. And so you would do system modeling exactly like this. Mechanical engineers do it, electrical engineers, all different types. But second order system is the last one we'll go to, because a third order system will consist of second order system and a first order system, or 3 first order systems. A fourth order system consists of 2 second order systems, or a second order system and 2 first order systems, or 3 first order systems. You can just keep going on and on and on, and it doesn't increase. You don't get more parameters to calculate. Those are just the systems that we have. I'm going to give you this table. You're all for pro at block diagram math now, right? And if you remember, the whole concept is moving points. What are you moving your points, or which way are you moving your points? Are you moving a point in front of or behind a block or a summing junction? So those are the harder ones. The easier ones are number 1 in cascade. That's a pretty easy one. Number 2, combining systems in block form. And then the only one that's not on here, do you see it? What's the only one that's not on here? I didn't include it because we do it so much, you're probably sick of seeing it. Feedback, right? Either positive or negative. If it's negative feedback, right? If it's positive feedback, those two. So that one I didn't include in the table because it's so important. It should be burned in your brain, but we do it a lot. Okay. That one should be pretty obvious, but yeah, just going through and looking at these tables, because the whole purpose of doing block diagram math, remember, it's easier to take a complicated circuit and break it down into smaller pieces and analyze the small pieces, and then come up with individual block diagrams for those small pieces. and then add on additional parts of the circuit, whether it's an electrical circuit or a mechanical circuit, and then you have an overall system which has maybe 50 blocks. But if I got to analyze that to set some performance criteria, then I've got to go ahead and find that characteristic equation. So I have to do block diagram math to be able to pull that important information. So the only reason why we need to do block diagram math is really because it's very difficult to come up with a transfer function of a system in and of itself. But it's easier to come up with a transfer function of an RL or an RC circuit, right? Or a voltage divider circuit. But if I had 50 voltage dividers, it would be very difficult to solve for that. And we talked a little bit about it when we were doing state space modeling, when we looked at each individual point in block diagrams, and we did mechanical systems. We're not going to discuss it necessarily here, but that's part of the advantage of using state space. Get that. Our last topic for the test, Routh-Hurwitz. And this is just a process or a procedure, right? So the procedure is as shown. Find the highest order S term. So look at your characteristic equation, and whatever the highest order S term is, then that becomes our first row in our Routh-Hurwitz tabulation. Then we start identifying coefficients. You take the highest S term coefficient, then we skip, go to the next one, and on and on and on until we fill out the first row. The second row is going to be subtracting 1 from the highest S row that we have, and then taking the next coefficient. That's an order. So instead of, let's say, S to the 5th, we take S to the 4th, and then we skip again, and we go from there. And then we actually do the Routh-Hurwitz tabulation. So that's what we have, which is using the determinant approach. I'm not going to re-specify it here, but you get the idea. If we terminate early, if we have a column that has a 0 in the first, if we have the first column in any row is 0, just the first column, then we substitute E. And then we continue on our results. And then at the end, we allow E to approach 0. That's not a sign change. 0, I guess, technically has no sign, right? It's neither positive nor negative. And so if you want, and the Routh-Hurwitz tells us the number of poles in the right-hand half plane are determined by the number of sign changes. Going from a positive number to 0 is not a sign change, right? Because 0 doesn't have a sign associated with it. And going from negative to 0 is not a sign change either. So that's why we were allowed to use this E term, just because we want to make sure that we don't end up with infinity as a number. We can go ahead and do the calculation. That's the first case. The second case is we have an entire row of zeros. This approach isn't going to work. And so basically, when you come across the case, we have a row. I mean, the first column is a 0. You're going to go ahead and do the next term in that row and check to see if it's 0. If you end up with a 0, then you've got to have a row of zeros. And that's when you use the auxiliary equation. You get the coefficients from the auxiliary equation by going one row up of what you're tabulating. And then whatever that coefficient is, or that row is, you use that coefficient and multiply it by the row name that you have. And then just like we did when we built the row Routh-Hurwitz, we skip a number and then we go from there. I've never seen, so I can't say this definitively, but I've never seen a case where your row of zeros has ever been in a row other than an odd number. It's always in an S to the 1 or an S to the 3. Okay. So then you have that auxiliary equation. Now you take the derivative of that with respect to S, you're going to get coefficients, and those coefficients become your next S value, your next row, if you will. Normally, when you have a row of zeros, you're going to end up with a marginally stable system. Okay. So Routh-Hurwitz doesn't tell us if the system is stable or not. It just tells us the number of poles in the right-hand half plane. If there are poles on the j omega axis, the Routh-Hurwitz approach is still valid because there are no poles on the right-hand half plane. So that's where you got to be careful. If you end up with a row of zeros, you're almost certainly going to have a marginally stable system. Okay. But that's helpful too, to go ahead and define or solve for what the poles are on the j omega axis. And you have that auxiliary equation. If you take the roots of the auxiliary equation, you're going to end up with complex roots. And that's actually what's on the j omega axis. So if you have to go ahead and use it for design, Because again, we would never do Ruth Hurwitz if we had coefficients. We just go right to MATLAB, right? Why would you use Ruth Hurwitz to figure out the number of poles in the right half plane? If you had all the coefficients, you can plug it into your calculator, or you can do it in MATLAB. This is just if your value, one of your coefficients is an unknown variable. You can't plug that into your calculator or MATLAB and get a result. So that's why I'll use it as a design parameter. So here are the questions. If I give you a characteristic equation, determine the number of poles in the right-hand half plane. Hopefully you're reading this and thinking about how to tackle this problem. Number two, if I give you a characteristic equation with adjustable parameters, specify the range of parameters so that the system remains stable. Okay. C, if I give you a block diagram, be able to do enough math to be able to obtain the characteristic equation and specify parameters to meet design criteria. So that could be first order system, second order system, or that could be Ruth Hurwitz, right? Just depends on what the question is. D, do block diagram math. That's very specific. And then E, if I give you a second order system, find parameters, right? So you should be thinking about what parameters you need to solve. And that's pretty much exam 2. Questions? Yes, sir.
So when using MATLAB,
MATLAB.
or, yeah, sorry.
Okay.
That's, I didn't know.
It's actually, it's interesting because you would think you'd call it MATLAB because it's made by MathWorks.
Yeah,
But I think MATLAB actually came from the concept that it's a matrix laboratory. So that's the software originated, because if you think about it, right, everything in MATLAB is essentially a matrix or an array. And so I'm assuming that's why they call it MATLAB, not MATLAB. But go ahead, sorry.
so let's say you're trying to see some characteristics of a transfer function that you have and you want to plot it. Can you use simulate plot?
You can, yeah.
Yeah, okay.
But I don't know how it's going to help you in the test, because the test is not going to say, you know, you can't just say, oh, from Simulink, here are the results, right? I'm trying to check your knowledge. So if you want to validate your results, and you can do a Simulink and just say, yes, is it stable or not? I mean, you do have the ability to draw pole zero maps right in MATLAB. You do have the ability to check stability. You have the ability to do all that stuff. It's just a question of, you know, I don't want to see if MATLAB can do it. I want to see if you can do it. So again, just to reiterate, MATLAB is a calculator. So if you just say from MATLAB and here are your results, would you write that on a test and say from my calculator? No, you would show your work on paper, and then you would do the calculations, and then your calculator would tell you the numbers. That's basically what MATLAB will be for the test. It's just going to give you the numbers.
Yeah, just kind of wanted to see if I could go in and improve my work, I guess.
I wouldn't prove it. I would just validate it. So if you want to validate it and say, yep, this is right, this is wrong, that's fine. But again, you get an option, right? You get a calculator or MATLAB, not both. Yes, sir. Well, zeta and omega sub n and omega d, right? That's in here, it's specified in here, isn't it? It's highlighted. You have zeta, omega sub n, and omega sub d. Pardon? I mean, you're welcome to look at it, but it's right there, right? There's only the 3 parameters. If you need to, you have these other 3 equations, right? Percent overshoot, T sub P, and T sub S. Did that answer your question, or? Okay. What else? This is the downside of having the exam review this far away from the test. How much studying have you all done? Not much? It's okay. You got 6 days. So the problem is you don't really know what you don't know, right? you're just getting this information like, oh, I don't know, but now I got to start thinking about what is going to be on the test and how I need to study. And some of you have a test with me in a couple hours, so you feeling good about this one? Yeah. The nice thing about the control system stuff is it's all just a lot of process stuff. You know what I mean? It's like just do the process and you get results. Go ahead. Yeah. Yeah. Yes. Well, in the other class that I teach, it's a lot of circuit analysis that you've built up, right? Hopefully over 3 so years of school. But again, this control systems class is really good, in my opinion. Myself on the back, because you can get 5 to 10 points on the FE just by doing these process things. You'd be better off to study your control systems part than your circuit analysis part, because some of these circuit analysis, you can spend a lot of time trying to learn it. In control systems, bada bing, you get the answer really, really quick. You don't have to spend a lot of time. It's like the answer just kind of appears very, very quickly. So that's the nice thing about control systems, I think. What else?
Are you just gonna like ask us if it's just a stable system?
I might ask if it's a stable system, but Ruth Hurwitz doesn't tell you if it's a stable system, does it? Ruth Hurwitz tells you the number of poles in the right-hand half plane. So if I said if this, go ahead. Yeah, what about the case of marginal stability? So if I ask, is this a stable system? And you do Ruth Hurwitz and you say, there are no sign changes in the first column, that doesn't necessarily mean it's a stable system. Right? Another way to ask the question about a stable system, remember, does any coefficient vanish? Right? So if you have s cubed term, s squared term, but no s to the 1 term, but an s to the 0 term, that's automatically an unstable system. Or if there's any sign change in the characteristic equation, s squared plus 2s squared minus 5s plus 1, unstable system. So that would be even easier if I said if the system is stable or not, and you can use either one of those conditions. Yeah, you can do that really quickly. But Ruth Hurwitz only tells you the number of poles in the right-hand half plane. I know it sounds kind of silly, but I'm just trying to be very precise because, you know, I don't want to have any confusion of what Ruth Hurwitz can do for you. But what else? You guys said you're going to be in my office right after. Why don't you ask your questions now? You can help out your classmates. Oh, power question. Sorry. I forgot about that part. Okay. Nothing else? How about in TV land? Usually I see some faces or two smiling, but not today.
The bad hair day.
Bad hair day? Ah. Every day for me is a bad hair day, so we have gray hair, but you all will be there someday too. Hopefully. Which means you've achieved old age enough that you can get gray hair, right? It's not a bad thing, it's a good thing. Nothing else? Yes, sir. Yeah, this is also, if you're not sure what this is under today's class content folder. So I'm not making this so that you can't access it. You have full access to the PDF. So if you want to look at this at a later date and print it out, you should be able to access it, just like all my other presentations. So what I'm suggesting is if you don't have to copy this down unless you really want to. It's up to you. I try to take my classes. So some of the theories in my classes, the beliefs I have in my classes, I don't want you to just do busy work. That's why I do the presentations in advance. So you can just write stuff in. I'm not expecting you, because one of the things I found when I was taking classes, I'd spend all this time copying the material over, but I was basically a stenographer. I wasn't learning. I wasn't following along other than just writing things down. And so I actually had to go back and look at my notes to figure out what the hell was going on. So I try to avoid that as much as possible. Anything else? Going once, twice. All right, sold. Have a great rest of your day. And if I don't see you, have a great weekend. And we will see you next week. Take care, everyone.
Football.
Thank you.